So guys, here we go. The date today, if you keep track of such things, is the 20th. The topic for today is titrating buffers. So guys, I'm taking your pulse right now, and I'm getting the sense that there's the potential for distraction today. And it's not just the food. I get it. So these guys that ride these 3-week, the Giro, the Tour de France, the Vuelta, there are three-week bicycle races in Europe every summer. And during the course of these 3-week races, they actually get 2 rest days. And these are days where there's no racing. They literally just lay over in their hotels and they rest. And guys, these are the days in the races that the guys dread the most. They would much rather climb 15,000 meters up in the Alps, and they do that some days. Meters, not feet. They would rather do that than sit in their hotel rooms. Because guys, what happens is when they sit in their hotel rooms for the day, their bodies actually slip into what they call recovery mode. And they dread that, because if their bodies slip into recovery mode, they get on their bikes the next day and they're just shot. They got nothing. So guys, on their rest days, typically they ride between 3 and 4 hours. They're not like full gas, wide open, going crazy, but they don't allow themselves to sit still, because if you sit still, you start to go into recovery mode. Guys, I started to go into recovery mode yesterday. Did you have that experience where you got up this morning and you're like, oh, I thought it was spring break, or frankly, I think my body thought it was summer vacation, even though it snowed, right? You know what I'm saying? You got up this morning and you were like, really? I thought we had the whole week off, or I thought we had the whole whatever it happened to be. And guys, we sort of slipped into recovery mode. We got to be careful, because what we're doing today is not something that's going to be well. It's not going to go well if your body's in recovery mode. Your brain is in recovery mode. So instead of that, guys, it's race time. Sorry, I promise you I didn't plan to do this. It is actually iRace time. Because guys, what we're going to do is we're going to take the ice box and we are going to make it into something new called an iRace box. I promise that was not in any way planned. But guys, today is going to be interesting. Today is going to be challenging. And if you're in recovery mode, today's going to be ugly. So you need to take this opportunity right now to get the calories in if you need, and stay focused. So let's see if we can dig into this. So guys, as we dig into this, we need to understand the word titrating, because if you guys are typical, that word titrate has such a tight definition to it that all you can picture is this process of adding a base to an acid. Which we are going to go and do in lab in 3rd period. But guys, what is titrating? Have we talked about it? What does titrating mean? We don't know. Yeah, and it's not even neutralizing. Guys, it's interesting. My brother, who is a neurologist, deals a lot with migraines, deals a lot with people with MS. And other neurologic disorders. And my brother will actually talk as a neurologist about titrating his patients up and down on different MS medications. And so when he talks about titrating his patients up and down on these drugs, and this is why it's so important that you follow the instructions when your doctors put you on meds. Guys, it's not just here's a drug, put it in your body. It's here's a drug, and we are going to add it in an orderly fashion so that we can not only get the drug in, but get the drug in a controlled manner. And if you care to know, there's a thing called the therapeutic range, and that's actually what they're shooting for. They're trying to bring the concentration of this drug in your body up to what is called the therapeutic range, and then leave it there, and then they bring you out. But guys, titrating is actually this process of literally adding or removing, if it's a drug, but adding something in an orderly fashion. Does that make sense relative to what you thought titration meant previously? Because think about titrating. You did it on the computer. You've got a burette, you've got a beaker, you've got a stirrer, you've got a nozzle, and you open this thing up, and you're adding something in an orderly fashion, right? So guys, that's what we're doing here. It doesn't mean neutralize. It doesn't mean acid-base chemistry. It doesn't even need to mean pH. It simply means adding something to something else in an orderly way. Okay, so what are we going to do when we titrate buffers? Well, we're going to add something to a buffer in an orderly way. So guys, now we need to review buffers. So what are buffers? When you picture buffer, what important chemical concept are you thinking? Common ion effect, right? You've got a weak electrolyte, and I think, can I do this? So we've got this, right? We've got a weak electrolyte, in this case the base, ammonia, and to that we add an ammonium salt, because remember that is our common ion, and when we do that we create these reserves, if you will, of acid and base, or of weak electrolyte and conjugate salt, and that's all about the chemistry of buffers. Does that ring true with you? Okay, so guys, with that said, maybe, would you let me review with you for a minute? Is that okay? Guys, let's do this. Grab your notes and let's actually do this. This I don't think is going to be a waste of time. So this isn't in your notes. I frankly wasn't planning on this. Let's use the convention that Kami got us thinking about. But here we've got a vinegar solution. Are you okay with HAC being vinegar? If you're not, figure it out. Jordan, I need you, buddy. Okay, so we're picturing a jug of vinegar, right? And should we draw the jug? Let's not draw the jug. Okay, so we got a jug of vinegar sitting here like this. Is this a buffer? Is a jug of vinegar a buffer? It is not. Why not? What's missing? The cation, the common ion, the conjugate base, the ion in common. So guys, and this was where Isabel started asking questions during homework, what salt could we then add to this weak electrolyte to buffer it? Sodium acetate, lithium acetate, rubidium acetate, strontium acetate, all those acetates, right? Okay, you just fell silent, and that scares me. You okay? Yeah. Okay, so now we've got a buffer. And guys, pH does not change with the addition of both an acid and a base. So guys, in order to have the pH conversation, where do we train our focus? What do we look at? The hydrogen ion. Because remember, this is what pH measures, right? Now I'm really getting scared, guys. Did you not bring anything forward from what we talked about last time? Okay, this is making me a little nervous. So guys, we are going to look at that hydrogen ion, and if in fact this is a buffer, that should not move. So a buffer can not only resist the addition of a strong acid, but also a strong base. So you ready for the tie back? We can add an acid to this, or we can add a base to that. What do we call the process of adding an acid or a base? Titrating. That's what we're going to study today mathematically. Let's talk about it again conceptually right now. So guys, let's just fill this all in. We can do an acid, we can do a base. So let's do the acid first. So guys, when we add an acid, HCl, HNO3, doesn't matter. When we add an acid to our buffer, when we dump hydrogen ion into the solution, why does the concentration of hydrogen ion not go up? Go ahead. But by what? Who grabs the hydrogen? The acetate ion. And the acetate ion goes, I got this. And the acetate ion grabs the hydrogens and converts it into unprotonated HAC. And as that happens, the hydrogen ion concentration doesn't change much. We're going to talk about much in just a minute. Because, guys, it will change a little. Why does it change a little? And let me just show you. This is where we're going today. Guys, when we do this, what happens to the concentration of HAC? Goes up. What happens to the concentration of AC minus? Goes down. What does the Le Chatelier's principle say that will do to the equilibrium? Shift it to the right. And we will produce a little bit of hydrogen ion through the dissociation of the additional HAC that was formed. Just a little. But not as much. And we'll talk about little and much in a minute. Okay, if this goes up, what does Le Chatelier's principle say? Same side does the opposite, opposite side does the same. So if this goes up, then this goes down and this goes, if this goes up, then it'll shift this way. So if this goes up, opposite side does the same. Now what if you focus on the AC going away? So if this goes down, same side does the opposite and this goes up. So both of those factors makes this get created a little bit. No, it's shifting right. Because if this goes up, there's more of this to break apart and that shifts the equilibrium to the right. I think your teeter-totter analogy is failing you. Yeah, get rid of the teeter-totter. A in equilibrium with B and C. If A goes up, what happens to B and C? They go up. Opposite side does the same, right? Okay, so hold on. Let me do that. Okay, so now let's do that again. So now what if B goes down? Same side does the opposite. Opposite side does the same. Okay? Yeah. You need a new teeter-totter, girl. You want to go back to that? But there isn't less acetate ion. Oh wait, yes, there is more acetate ion. So as you draw down the amount of acetate ion, what does the reaction want to do? Make more. And it does that by breaking this apart, moving the equilibrium to the right. Right, so both changes, keep your eye on this. Okay, keep your eye, get off your teeter-totter and keep your eye right there, okay? Don't worry about this. Just talk to me about this. If this goes up, what's that going to do? Go up. Now, focus here. If this goes down, what is that going to do? Go up. So both of those changes are leading to the production of more hydrogen. And they're both happening simultaneously. The addition of the hydrogen from the strong acid makes this go down and it makes this go up simultaneously. And both of those changes lead to the production of a little more hydrogen ion from this dissociation. But understand, it's nowhere near the amount of hydrogen that's dumped into this thing by the strong acid. Because remember, acetic acid only protonates, 0.7%? So for every 100 hydrogen ions that you put in, you'll get 0.7 of a hydrogen ion back out. Because it's less than 1% protonated. Is that okay? Correct. But I told her not to. She's on her teeter-totter. Yeah, so what we're going to do is we're going to keep an eye on pH. And so here's what we've set up until now. We said when we dump acid into the solution, okay, when we dump a strong acid, HCl, but we don't care about the Cl, when we dump a strong acid into the solution, the H bonds to the conjugate base, the acetate ion, and it forms this. And we've said that this cycle happens and this doesn't change. That's what you walked in here this morning understanding. Now what we're saying is that is not completely the case, because what happens is as this cycle is happening, we are making more HAC. And Le Chatelier's principle says as we make more HAC, a little bit of it, 0.7%, but a little bit of it will break apart and make a little bit of hydrogen ion. There isn't, no. So this H plus isn't this H plus.
Well, yeah, I know. But it's as it's from the HAC.
Right, but understand, but what you said is if there's more HAC and more H plus, which ways, but that's not the case. So the H plus that we're adding turns into HAC. Now we've got more HAC, and because we have more HAC, a little bit of that will break apart and make more hydrogen ion.
Because, like, in my mind, you know what it's like, it will say on my phone or something,
Mm-hmm.
less of this, and, like, chalet or whatever.
Yeah, right.
But, what I'm just confused on is I'm thinking of it as having less acetate ion, not as more.
No, I understand what you're, and so here's what you've got to do in your brain, and this is what this, guys, and you'll notice, I love, we're just letting Catherine run with this, and I love that you have the confidence to do this, because what you're doing is you're running us straight into the math that we're going to do today. So what you've got to do is you've got to, and guys, this is to all of you, what you've got to be able to do is tease these two processes apart. So this is process one. This is dumping the acid into the buffer. This is process one. Process two is the buffer then restoring equilibrium. And that's literally the way that this happens. Let me clean up the mess. So we've got HAC, and the HAC breaks into AC minus and H. And guys, this is all the chemistry that you're going to learn today. So if you're sitting here going, this is Catherine's issue, and I can ignore it because it's just Catherine's issue, this is all of our issues because Catherine's actually thinking ahead to what you're going to learn today. And I'm not going to explain it, not now. I'm not going to explain it again. I'm going to teach it to you now. So guys, don't look away, because this isn't just let's talk to Catherine. This is let's learn some chemistry. So guys, this is what you've got to do. You've got to break these two processes into two separate things in your brain. So what we've got right now is our vinegar, and let's say that we've added some sodium acetate, and this is now buffered. So now let's switch colors. So now we're going to switch, and we're going to add hydrogen ion to the buffer. So just focus on this. Just focus on this, okay? So what happens when we add hydrogen ion to the buffer? It goes this way, right? So all we've talked about is that strong acid, and it's a strong acid. Strong acids don't do equilibrium stuff. They come in and kick butt. So guys, for every molecule of HCl that we add, one of these dies and one of these gets born. It is literally a strong acid gobbling up the conjugate base and converting it into unprotonated acid. And this isn't any of that mamby-pamby equilibrium stuff. This is full-on hydrochloric acid destroying acetate and turning it into HAC. And it causes a big old mess, because what happens is the concentration of this goes down. Where does it go? Well, it gets turned into this. So this strong acid comes in, kicks butt on the acetate, and converts it into acetic acid. And as we add more acid, that just keeps happening and happening and happening. And then eventually we stop adding acid. And guys, when we stop adding acid, is this system at equilibrium? No, it got its butt kicked. It's got way more acetic acid than it needs and way less acetate than it needs. Stop right there. Does that make sense? Can you see it? So guys, let's do this again. So we've got this buffer, right? We've got a concentration of this, and we've got a concentration of this, and they're at equilibrium, and they're hanging out doing their equilibrium thing, and everything's good, and they're enjoying themselves, and life is good. And then, oh crap, here comes hydrogen ion. And hydrogen ion comes in here and goes, woohoo! And it just rips the bajinkers out of this equilibrium. And all of a sudden, this is going away, and this is getting made. And is it still at equilibrium? No. So when does it stop? When does the carnage end? And the answer is when we stop adding acid. So now we've added all the acid that we're going to, and we've got a mess because this thing isn't at equilibrium anymore. So let's talk about where it is. What about relative to HAC? Does it have more or less than it should at equilibrium? It's got more. What about AC minus? More or less than it should at equilibrium? Less. So what does this buffer want to do? What does this equilibrium system want to do? Just like the tubes. It just wants to go back to equilibrium. Well, how does it go back to equilibrium? Well, it's got too much HAC. It's got to get rid of it. It doesn't have enough AC minus. It's got to make more. So which direction does the reaction go? This way. It's got to get rid of this and make more of that, and it can do both simultaneously by getting rid of this and turning it into this. And as it does, as a side product, if you will, it makes some hydrogen. But guys, how much of this takes place? Well, 99.3% of the new HAC isn't going to fall apart. Because we found out a couple of days ago that acetic acid only protonates 0.7%. So we're going to make 0.7% of this and 0.7% of that. But 99.3% of the acetic acid is not going to fall back apart after it's been formed by the addition of the acid. And so this will go up a little, but not as much as this, because for every 100 of these that we put in, 99.3% of them get tied up as acid, and only 0.7% of them get re-released as hydrogen ion. Holy smokes. Better? Does that make sense? Don't get us off track. Okay. Because, keep going. Why?
Because they make a low percentage.
Right, they do this less, right? The lower the Ka value, the less they want to break apart, and the less drastic the reestablishing of equilibrium is. Did you catch that? That's exactly the point. That if you've got a weak acid with a big Ka, it's going to break apart quite a bit and give a lot of hydrogen back to solution. Those low Ka weak acids are the ones that are good buffers because they don't break apart as much. Do you get it? So guys, here's then the way we're going to deal with this. So guys, and I hope you like the way we talked about this. We're going to separate this. This chemistry right here, which is adding the strong acid to the buffer, this is not an equilibrium process. This is full-on quantitative chemistry. For every molecule of this that you add, actually make sure you catch this. For every molecule of this that you add, one of these goes away and one of these gets formed. Now guys, what you're going to find out is that because that is not equilibrium chemistry, these calculations are going to be done in moles. Because moles are counting groups. How many atoms did you add? That's how many molecules get converted. So those calculations are done in moles. They are not an equilibrium process. They are simply counting. Add 1, kill 1. Add 2, kill 2. Add a mole, kill a mole. It's literally a mole process. But then, guys, we've got to talk about this. The reestablishment of equilibrium. And as we talk about the reestablishment of equilibrium, this is now a reaction rate issue, right? Because the concentration of this goes up, more things to react, pushes it in this direction. So guys, equilibrium are always molarity-based calculations. Do you get the idea? So and Catherine, that's why I was pushing you to say separate these in your brain, because I think you were trying to think about them as being the same, and your seesaw was busted, right? But that's really and I almost talk more about your seesaw. I don't want to do that. What I was picturing was, what if you had your seesaw and took some rocks over here and moved them over here and then but don't do that, because it could be total. Is we are going to separate the moles, that is the adding of the strong electrolyte, from the molarity calculations, which is the reestablishment of equilibrium. Because guys, if you think about it, when we've done ice boxes, what have all the units been in the ice box? Molarities, because ice boxes allow you to study equilibria. What we're going to do is we're going to expand our ice box, and we're going to allow it to study this breaking of the equilibria by adding a strong acid or base, and then the reestablishment of equilibria. Does that make sense? Okay, so guys, if you printed the notes, I am going to jump out of them radically. Let me just show you. So guys, this is where we should go next. Let me just show you. So the first conversation that we should have is about the capacity and the range of buffers. But that would be a total distraction from what we're talking about currently. So I'm going to switch the order of these. Where's like this. And guys, we are going to jump right in to titrating buffers. So here we go. You may want to write this down. So what we're going to do right now is we are going to look quantitatively at how buffers respond to the addition of strong acids and bases. So if and as you're writing that down, guys, think about what you're writing. So buffers respond. Remember, buffers are common ion effect, right? They're weak equilibria that have been hopped up by the addition of a common ion. But now, guys, we're going to add to this buffer a strong acid or a strong base. And some of you may be thinking to yourself, couldn't we also add a weak acid or a weak base? And the answer is yes, but you can't study it without calculus, because you've got two competing equilibrium affecting the other, and then it becomes like a related rates problem. I'm glad that you groaned. So we don't have to do that. So guys, in AP chemistry, which is general college chemistry, the only thing that you have to be able to think through mathematically is take a buffer and add a strong acid or a strong base. What's special about strong acids and bases? They aren't equilibrium processes. They are quantitative processes where you're just killing stuff. So we don't have to get into the related equilibria, because that's nasty. So guys, in order to do these calculations, we're going to make two assumptions. Now guys, the problem here is that while these assumptions will make sense, they won't mean as much to you because we switched the order that we just were to do today. So assumption number one is this: we haven't exceeded the capacity of the buffer. We'll talk more about that at the end of the day. Fundamentally, what that means is we just haven't run out of any of either the conjugate base or the original acid, I guess, or the original electrolyte. And then guys, assumption number two is this: the acid reacts completely with the buffer. But what is it that allows us to assume that that's going to be the case? It's strong. We're always going to be adding strong acids and bases, and therefore number two is covered. All right, so guys, with that said, it's time to jump into the fun and exciting world of IRACE calculations. I would like to take credit for this, frankly, because I can. If you look in the book, chapter 17, or if you look in the, when you get your Princeton books, guys, they do this differently. Other resources will not show you IRACE boxes. I made these up. To my knowledge, I think I made these up. Guys, what they'll show you is they'll show you two separate sets of calculations. One calculation is the quantitative reaction of the acid with the buffer, and then the second calculation is the reestablishing of equilibrium. What I found was that, with my students anyway, it made more sense to put them all together in one singular structure. And I call these I-race boxes. So guys, we are going to learn to solve these two-step problems using what I call an I-race box. And it goes like this. The first thing that we study is the acid-base neutralization. So we've got a buffer, we add a strong acid or we add a strong base, and that thing neutralizes part of the buffer. Guys, this is a particle-dependent process, and therefore the calculations have got to be done in moles. Now, as you do these calculations, we are going to start with I, which is initial, just like ice was initial. But to that, we're going to add an R, which stands for reacted. So here's how this is going to go. We're going to go, okay, I know how much, I don't know, acetic acid and acetate ion I started with in moles. And then I can figure out how much of this stuff got reacted because I can figure out how much acid or base I added to the buffer. Once we've done that, then the rest of the calculation becomes about reestablishing equilibrium. So guys, then what we're going to do from there is we're going to use Ka and the newly adjusted concentrations of acid and conjugate base from step 1 to calculate how much hydrogen ion was produced by the dissociation of the weak electrolyte. And as Daniel pointed out, the weaker the electrolyte, the less it gets produced. But this will then change pH slightly. This reestablishing of equilibrium is a molarity calculation because equilibria are dependent upon rates and rates are dependent upon concentration molarity. Now guys, as you do this, you will then go adjusted, but you got to be careful. Watch your volume changes. This is the tricky bit. So the A in I-race is adjusted, then C is change and E is equilibrium. So basically what we've done is we've taken an ice box, we lifted the I away from the C, we added an R, we added an A, and we're going to go from there. Remember, the first calculation needs to be done in moles because it's a strong acid. It's a strong acid or base we're adding. It's not an equilibrium process because it's strong. And then the second part of the calculation, the bottom part, is a molarity problem because that's an equilibrium system. And so along the way, we've got to convert moles to molarity and be careful of the volume. So guys, what we're going to do is we're going to solve 1.5 of these. And then we're going to go back and talk about the capacity and the pH and the capacity of buffers, and then we'll wrap up the day. You guys ready to go? Is that okay? Okay, so guys, let me show you a sample problem. It reads like this. A buffer is made by mixing 100 milliliters of 1 molar acetic acid with 100 milliliters of 1 molar sodium acetate. Pause for a second. Could you have almost predicted how that sentence was going to play out? You've got your weak acid, acetic acid. You've got your common ion salt, sodium acetate. Hopefully that first sentence just felt familiar. We've built a buffer. They give you the Ka of the acetic acid, which frighteningly many of you probably have memorized. But now, guys, we're going to dump a strong acid in, and then we'll do a base, but we'll do a strong acid first. So So guys, the question is this: calculate the pH of the solution when 50 milliliters of 1 molar hydrochloric acid is dumped in this thing. You guys good? Okay, so here's what I want you to do. All right, let's do this. Doesn't need to be big. You need a beaker. And guys, in your beaker, represent your buffer. Don't include water, but represent your buffer. What is in your buffered solution? Did you get it? And what I'd like to do, guys, is I'd even love to talk numbers with you. So here we go. So we've got some acetic acid in there, right? Is it dissolved? Yeah, all of it. All of it's dissolved. But that's not all we have in there. What else do we have? Got some acetate ion. What else? We got some hydrogen ion. What else? And some sodium ion. So guys, now let's talk about how much. So I know it's 1.00, but let's just call it 1 molar. So guys, how much acetic acid do we have in solution? How much do we have? No, let's do it in moles. How much do, let's not even do moles. Let's do molarity. What is the concentration of our acetic acid in solution? So 1 molar, except for what? Let's even talk about it before it's buffered. But you're not wrong, Brandon, but maybe we should move into it. So guys, what is the concentration, before we buffer this, what is the concentration of the acetic acid?
It's 0.99.
So it's 1 molar minus the 0.7% that falls apart. Is that okay? Okay. So guys, what is our concentration initially? Well, before we buffer it, what is our concentration of acetate ion? Yeah, however that works out, it's functionally none, right? It's very little. Yeah, sure. So then we add the sodium acetate, right? And then what does the concentration of the acetate ion become? 1 molar plus, right? So it's 1 molar plus the amount of acetic acid that breaks apart. Does that make sense? Okay. Then, guys, we've got our hydrogen ion. What's the concentration going to be? Pretty small, but still not 0. And then we don't care about our sodium. Now, what if we wanted to know the pH of this buffer? What would we do? Last time's homework, right? Can you picture it? That we would lay out the equilibria. You know what? We're going to have to do it anyway. We may as well do it. So, guys, we would lay out the equilibria. Go ahead and do this with me. Is that distracting to have the beaker over there, or am I okay? Is that okay? Okay. So, and guys, we're not going to do this because we've done this, but let's talk about how we would do it. What if we wanted to know the pH of the buffer? Well, we would go ice, and we'd go 1 molar, 0, minus x plus x plus x. Can you picture it? You okay? Then it's all the Ka expression. Is that okay? Okay. And we could do that. And we could figure out the pH of the buffer. Okay, now guys, what we're going to do is we are going to figure out how this buffer then responds to the addition of 50 milliliters of hydrochloric acid. And here's how we're going to do this. And I'm going to switch colors. And guys, please don't write. I always do this wrong. So please don't write until I have a chance to think about it. So I need to go, you'll see why this is different in a minute. I see, where do I skip the line? So C, and then here. Okay, so we're going to go, oh no, IR. Sorry. IR. Skip a line A, C, E. Guys, skip a line between the R and the A. Hold on, let me think. So bump. Yes. Guys, skip a line there. Skip a line between the I and the R. Or, sorry, the R and the A. So, guys, well, no, let's do this. Here's our context then, right? So we've got our buffer. And what we're going to do now is we're going to add some HCl to this. Again, our Cl doesn't matter. What we're going to add is some H. And we're going to dump this hydrochloric acid into our buffer. So guys, let's go ahead and represent, and I would strongly encourage you to do this in homework and the test. Guys, let's go ahead and represent that right here. We're adding hydrogen. Now when we do, what chemistry is going to take place? Who's going to grab those hydrogen ions? The acetate ion, and they're going to get converted into acetic acid. I really benefit personally from writing that out because it helps me remember the underlying chemistry behind how the buffer responds. It's just a great visual reminder for me. I think you may benefit as well. So guys, now that we've got all the pieces in place, we can now solve the problem because what we're trying to do is figure out the pH of this solution when the damage is done. So what are we going to do? Well, guys, in order to do this, what we're going to do is fill in the erase box. Now, guys, let's remember the chemistry. What's going to happen to the amount of acetate ion? When we add the acid to the buffer, what's going to happen to the amount of this? It's going to go down. What's going to happen to the amount of this? It's going to go up. How much is this going to go down, and how much is this going to go up? And the answer is not the same. It is the same, but that's not what we're looking for. How much will this go down, and how much will this go up? How much acid did you add? Does that make sense? Okay, but guys, the problem is this. This is not an equilibrium process. This is a strong acid. Strong acids don't mess around. For every one of these you add, one of these dies and one of these gets made. So this is not a calculation that we can do in molarities. This is a calculation that's got to be done in moles. This is where you have an advantage over me because you have more blank space. Because guys, we need to know initially how many moles of acetic acid did we have? And initially how many moles of acetate ion did we have? And that requires a secondary calculation, which I'm going to do here. So guys, how many moles, and you can do this down below, how many moles of acetic acid did we have? Well guys, we had 100 milliliters. And 1,000 milliliters is 1 liter, and 1 liter is 1.00 moles of acetic acid. That's way too many ones and zeros for me to keep track of. So guys, we had 0.100 moles of acetic acid. Did I do that right? I think so. Then, how many moles of sodium acetate did we have? I don't want to say the same, because you're always going to think it's the same. But in this case, It's the same. So guys, so long as we're having fun doing dimensional analysis, why don't we do all of the dimensional analysis that we need to do? So guys, the thought goes like this. This is how much acetic acid we had. This is how much sodium acetate that we had. How much of this is going to go away and how much of this is going to get formed when we add the strong acid HCl? As much as HCl we added. So guys, we need to also figure out how many moles of HCl is in 50 milliliters of that. So we may as well do that calculation as well, so long as we've got space to do calculations. And I know this is low on the screen, but you should be able to figure this out. 1,000 milliliters is 1 liter. 1 liter is also 1 mole. That's the beauty of being the teacher. You get to pick concentrations and volumes that make the math easy. And I lost significant digits, but now I didn't. Okay. So guys, what we know now is how much acetic acid we started with, how much sodium acetate we started with, and importantly, how many moles of HCl we added. So guys, let's take this information and let's transfer it to our iRace box. Ready? Can I go? Okay, so here we go. So initially, how much acetic acid did we have? 0.100 moles. Initially, guys, how much acetate ion did we have? 0.100 moles. Now, how much hydrogen ion did we have initially? None. Now, what does the R stand for? Reacted. So guys, how much acetic acid was formed through the reaction? What's the answer to the question? How much acid did you add, right? Because where did this come from? Where did more of this come from? From the addition of the hydrogen ion. How much hydrogen ion did we add? How much acid did we add? How much acid did we add? 0.05 moles. So this is going to be plus 0.0500 moles. How much of the acetate ion went away? The same 0.0500 moles. How much hydrogen ion was made? None. That's the whole point of the buffer. The addition of the hydrogen, and guys, make sure you see this, the addition of the hydrogen ion does not increase the concentration of hydrogen ion. It reacts with the acetate ion and forms acetic acid. Okay, now we can do the subtraction and the addition. So this becomes 0.150 moles. This becomes 0.0500 moles. And this is still 0. So guys, that's what the addition of the acid did to the buffer. Acetate ion died, acetic acid got formed. Now we are done adding the strong acid HCl. So what happens now? Now it goes back to equilibrium. This system is not at equilibrium anymore. The addition of the strong acid HCl messed up the equilibrium. So now this thing wants to get back to equilibrium. So now we need to put on our equilibrium goggles. And guys, when we put on our equilibrium goggles, what units do we need? Molarities. So how do we convert moles into molarity? Divide by the volume in liters. So guys, what is the volume of this solution in liters? 250 mil, and guys, make sure you see why. 100 milliliters of this, 100 milliliters of this, 50 milliliters of this. We have 250 milliliters of solution present. So what we need to do is divide each of these by 0.250. That's why I had you skip the line, because it gives you a place to write down the result of that math. So 0.15 divided by 0.25 is 0.600 molar. 0.05 divided by 0.25 is 0.200 molar, and this is still 0. The which? Adjusted. And Brandon, do you see why? These are the concentrations that were adjusted by the addition of the strong acid. Does that make sense? And now we're going to describe it going to equilibrium. So given our new concentrations, how does this thing get to equilibrium? Well, this is going to go away, and this is going to get made, and this is going to get made. So we go 0.600 minus x, 0.200 plus x, and x. So guys, at this point, I'm going to get rid of my beaker because I'd like to be able to try to solve this all on one page. So I'm going to have to write small, but I'm going to do it here. So how do we then solve for pH? So Ka is equal to acetate ion times hydrogen divided by unprotonated acetic acid, or 1.8 times 10 to the negative fifth is equal to 0.200 plus x times x divided by 0.600 minus x. And then that is approximately equal to, and I don't really have a way to write that well, 0.2 x divided by 0.6. Was that okay? Is that okay? What allowed us to get rid of the plus and minus x? It's insignificant. 1.8 times 10 to the negative 6 times 0.6 divided by 0.2. And I get 5.4 times 10 to the negative 6th molar. And guys, that is our concentration of hydrogen ion. So forgive me, I'm going to take a shortcut here. pH is the negative log of that number. Did I get it wrong? Oh, fifth. Sorry, I think I even said 5. My calculator says 5. That's a 5. So we're going to take the log. And guys, the pH of this is 4.28. Right. Yeah, and that's what I want to do, guys. Let's answer Matt's question, and then I want to talk. So are you okay with all of this? Okay, so then the question is, how good was that buffer? So we get that this system was approach that question would be to ask ourselves, what was the pH of the buffer before we dumped in the acid? Do you know what I'm saying? But guys, watch this. Let's see if we learned anything. We've got 0.1 molar acetic acid. I'm sorry, not 0.11. We've got 1 molar acetic acid. We've got 1 molar sodium acetate. We have a buffer where the weak electrolyte and the common ion salt have the same concentrations. And at that unique set of circumstances, what is true? pH is equal to pKa, right? So when those are the same, pH is equal to pKa, and we know that Ka is 1.8 times 10 to the negative fifth. So if we go 1.8 times 10 to the negative fifth and turn that into a pH, the pH of the buffer before we dumped in the acid was 4.74. So guys, we dumped in an amazing amount of acid. 1 molar acetic, or 1 molar hydrochloric acid. And the pH only changed from 4.74 to 4.28. That buffer did its job. Did the pH change a little? Yeah, but nowhere near as much as it would have if we had just dumped that acid into water. You get the idea? So guys, check this out then. What if we then hit the reset button and solved this question? How would the buffer respond? What would the pH be if we added 50 milliliters of sodium hydroxide? What would it look like now? Well, if we added sodium hydroxide, which direction does that shift the equilibrium? So it goes like this, right? So our negatives become positives, and our positives become negatives, and all the math is the same. You get the idea? Okay. So, guys, with that said, guys, this is the last thing we need to talk about. The character, do this for me. You don't need to write any of this down because you've already learned all of this. Guys, seriously, watch. I'm going to teach this flipped around for the rest of my career because it makes so much sense. Guys, check this out. When we talk about buffers, there's two important things that we need to talk about. One of them is the capacity of the buffer. So guys, the capacity of the buffer is the amount of acid or base that a buffer can absorb without the pH changing a lot. This depends on the amount of weak acid or weak base. Guys, that is what this is all about. So guys, this is our calculation we just did, right? What is the capacity of this buffer? 0.1 moles. What is the capacity of the buffer in the other direction? 0.1 moles. So guys, the capacity of the buffer is dependent upon the number of moles of weak electrolyte and conjugate you've got. That's all there is to capacity. The more of these things that you add, the greater the capacity of the buffer because there's more stuff there to deal with the addition of a strong acid or base. You see what I'm saying? So guys, what if we would have added, instead of adding 50 milliliters of strong acid, what if we would have added 150 milliliters of strong acid? It would have broke the buffer. Because then, going back here, guys, if we had added, oh gosh, that's from General Chem. Where did those notes go? Oh, you know what? They're here. Guys, if we had added, where'd they go? I hate that it sees these separately. Maybe I can't find it. It was? Oh. So where's the calculations where we figured out our numbers of moles? There. So guys, if we had added 150 milliliters of the acid, the strong acid, that would have given us then it would have given us 0.150 moles of strong acid, and that would have been more than the moles of the things that were buffering, and it would have brought the buffer. So in order for our buffer to stay intact, this number has got to be smaller than those numbers. If it exceeds it, the buffer breaks, and we call that capacity. Does that make sense? Okay. So with that said, that's the idea with buffering capacity. But here's an interesting question. Say that we have 1 liter of a buffer that's composed of 1 molar acetic acid and 1 molar sodium acid. Then guys, we have a liter of a buffer that is 0.01 molar in acetic acid and sodium acid. See what I'm saying? So what about this? Which one's got a better capacity, the top one or the bottom one? Top one, right? It's got more stuff. But here's an interesting follow-up question, which leads into the other idea. What are the pHs of these solutions? They're the same because the polarities are equal, pH is pKa. So guys, these would have the same the same pHs. It's just the top one would be 100 times better buffer because it's 100 times more concentrated. Does that make sense? Okay, so what do we do then with that idea of pH? Well, guys, let's talk about this really quickly. So when we have a buffer that has equal concentrations of our acid and our conjugate base, we know pH is equal to pKa. So there's another important thing that you need to keep in mind. Buffers tend to work best when the difference in these concentrations is within a power of 10. But because we're talking about logarithms, the important idea becomes this. Buffers usually have a usable pH range that is pKa plus or minus 1. So for example, when we looked at our acetic acid buffer, its Ka was 1.8 times 10 to the negative fifth, so its pH was 4.74. What that means is that this would be an effective buffer between about 3.74 and 5.74, because outside of that range you get such a difference in terms of these two concentrations that it's just not as effective a buffer. So it's just something you need to tuck away in your brain, that when you build buffers, the pH range of the effective pH range of the buffer is plus or minus 1 relative to pKa. Does that make sense? We okay? Okay. So, guys, that's it. Here's your homework. We're going to call it quits there. Take the time that you need for a break. Guys, when we come back, we will